Hello, people. Can you hear me online?
Hello, Dr. Salam.
All right. Can you see my screen?
Yes.
Thank you.
Welcome.
All right. We are gonna start with lecture notes first, and then we'll do the homework later, because I just wanna make sure that we cover this first. But we will have time for the homework, so don't worry. You will get the homework. Okay. So we said our project this year is going to be about designing a water heating system. And we have to do like at least 3 methods to basically be able to compare them. So the first one is going to be solar heater. So we're going to heat the load. And I was thinking that to make us feel that it's really realistic, it's very hard to imagine a house that will always get, say, 2 gallons per hour. Like, what is this kind of house that they always have the same amount of water? So if we do this, you guys will not feel that it's really realistic. But I was thinking, if we say that the load is a swimming pool, then it's believable that, and it's like not even like a home swimming pool, but like, say, Jenks High School swimming pool or aquatic center, a big water body that need to be heated all the time because people are using it all the time. So in the evening, they have like the school kids come, and in the morning, they open it for the community so that people can come. So that will be bigger load, but so what? We will just have a lot of heaters. But it will make us feel that, yes, that is a load that, from 8 a.m. until, 8 p.m., people expect that water to be warm and ready for them. Okay. So the first option would be just using solar heaters, and of course, electric auxiliary unit to support when the sun is not there. The second would be electric heat pump. What's electric heat pump? Air conditioning. Just like our home are heated by heat pumps. But that electric heat pump, we will run it with photovoltaic. And the third option will be just like natural gas water heaters. You fire the natural gas, have flame, and the water come, get heated. And any other option that you guys have the time and the desire to come up with. And I think I did for some of you, but maybe not all of you got this. The American Society of Mechanical Engineer, which is a national, actually international organization. You'll be amazed how many countries, foreign countries, have American Society of Mechanical Engineering chapters on them. But we have the national SME, and then we have the local SME in Tulsa. And actually, that section in Tulsa, it's called the Mid-Continent section. And it used to have jurisdiction all the way from Parksville down to Dallas, including Kansas and Arkansas. And it was like huge chapter, okay? So it actually celebrated its 100 years centennial like 2 years ago or something, okay? I was a chair last year, so I should know. But anyway, that section, for the first time, in order to spark innovation, they decided that they're gonna have a local competition between OSU Tulsa and TU and ORU, and what's the third school? TU, ORU, and OSU Tulsa. I think that's it. Those 3 schools, the undergraduate, if they are doing something innovative in their design project or course, or if some of the undergrad are doing research in the labs, you will get like you'll give 10 minutes presentation, or like maybe 15 minutes presentation. You present what's you're working on, what's your new idea is, and you will end up winning the title of the best innovative award. And the competition is gonna be not that hard because there's only 3 schools, and how many will come from each school? Maybe because it's the first time, maybe not that many people will show up. So what I'm trying to say is that the deadline is March 31st, which is in 20 days. But all you have to do is submit the abstract by March 31st, and then the presentation itself is going to be in April. So by that time, you will submit your project. So what I'm trying to say is that why don't you take a chance in coming up with something really new and innovative for heating a public swimming pool? Besides those three options that have been always used, like every single house is using one of those things to heat their swimming pool, you guys can really just this weekend get a peer and just like really get thinking, what is an innovative way to heat my swimming pool, okay? And maybe you will win. And imagine now the title in your resume, how that will do to you in your job interview when you say, yeah, I did win the American Statue Mechanical Engineer Award in innovation. That would be so awesome. Okay, and you don't have to do it, by the way, by yourself. You can do it as a team. And regarding the project, so the thank you for all of those who had responded to my question, what we should do in the design project in this course, which is only 10%, but still, it's important. I asked it whether we should do it individually or in a team or leave it to the students. And the majority of the people responded, say, let's make it, give the people a choice. So if you want to do it individually, you can do this. And if you want to do it in a group, you can do this. But that group, in my experience, more than 3 is just a mess. People don't have the time to collaborate and talk to each other. And actually, as a matter of fact, since this group is not really that big, I'm leaning toward just making out of 2. So because we don't really meet with each other that often because of the COVID and stuff. So having a 3 way phone call is really hard, or not as often that you do it as 2. So what I'm trying to say is that let's limit the team to 2 people. This way, it's super easy for you. Just make the call and pick the phone and call your friend and figure out, did you do this? Can you do the graph? It will go much faster. Of course, with 3, yes, the workload will be lower, but I'm just worried about the communication in our scenario over here. So project is going to be, if you want to do it alone, go for it. If you want to do it in a group, you pick someone else and work with, okay? That should cut your work by 2. And actually, I personally would recommend that you do it in a group. Even if you think that I got it, I know everything, I don't need someone else. Those people are way less smarter than me. Even if you are that person and you think you are the smartest person ever, I still think you will really benefit a lot from working with other people. Because chances are in real life, you will never be able to do a complicated project by yourself. And so there are all those soft skills about how to be nice to the other person, how you can motivate the other person. So you would learn from dealing even with a person that is not as active as you. You need those skills. You need to be in that scenario. And you do it now, and for what didn't work, you lose what? 5 points out of 10. You're not gonna get a 0, right? So you lose 5. So it's really very free price that you pay for learning. And what if it didn't really work? I mean, what if you really managed to communicate really that well with that person, and you guys really help each other? You gain a friend, and you get an amazing project. And maybe with putting your head together, you come up with very innovative design, and you guys will win the award, right? So it's up to you, but I would personally recommend. And I was one of those students that I think that I don't need anyone else with me. I can do it by myself. And my dream job when I was an engineer, I just wanted to be, my dream job was a submarine engineer. I just wanted to be in a submarine, in the engine room, just with the engine, taking care of the engine, and that would be the best job ever. So I understand when people don't like to communicate with others, because a lot of engineers are introverts, but that's not good. You need to be extrovert. You need to be able to communicate with other people and love other people. And every time you actually work with other people, in my experience, yes, there is this communication problem, but it's very rewarding. Good things happen when you find a good partner. Yes, bad things happen when you find a bad partner, but really, it's worth the risk. So if you are one of those things, so those people that think that you can do it by yourself, please put an effort to convince yourself. No, I think I'm gonna take a risk and work with someone else, and it will go work well. Okay. All right. So when we solve the homework today, you will be able to see how does you can. So really, what we are doing is sizing the. If you're gonna stick to those traditional solution, so all we need to do is just size the system. Huh? It's like if we're gonna buy this one solar heater in the homework, I bet there are better ones. So all the project is basically to make sure that how many of this guy will be able to satisfy or supply the load of that swimming pool. You know, it's not that hard. So next one is how do we use photovoltaic panels to generate the electricity to run a heat pump running that load, that heating load, okay? So here is this amazing picture from, I guess, France. And you can see a nuclear reactor in the back. And the photovoltaic, so as if they are saying, we don't need you anymore. We can just basically get the sun to run our house. So how does it work? And of course, this is really in the kind of under jurisdiction of electrical engineering and material science. People work on those things. But as mechanical engineer, we need to be able to understand, you know, how much area do we need, so that we can figure out basically how can we meet our heating load or electric load using something like this. So a little background that will be really interesting. It's not that hard for us to understand what's going on. So we need to understand that there is something called insulator, something called conductor. Conductor, you put voltage on them and electron run through. Copper, example. And insulator are the one that you put the electric voltage on them and they don't send electrons. The electrons are stuck. And those are like the rubber thing that you had on your tools, electric tool, right? So that when you touch the wire, you don't get shocked. So there is, now if you look at the atom side, like scale, those electrons are sitting in orbits around the nucleus, right? And for one electron to be able to move, need energy. And that energy is measured in electrovolt. Okay, so that's, we can convert electrovolt to joules, and we will do this, especially when we go to nuclear energy, because all the reactions are in mega electrovolt, and we want to turn this into joules. So we will learn how to transfer this immediately. That's not a hard problem. Anyway, so he's saying that if the energy needed to take an electron out of the atom and move more than 3 electrovolt, that's a lot of energy, and that's an insulator. If of course, conductor don't need any, like you just put a voltage, current will go through. So now if it take less than 3 electrovolt to make that electron move, then this is called semiconductor. So a semiconductor is really easy to send electrons through it, but you need voltage. Not as high as insulator, but still. We'll figure out how much is this. This is called the gap, band gap energy. Okay, how much energy does it take to convince one electron to jump? Where does he jump to? So here is the one of the famous semiconductor is silicon, right? And a lot of those wafers are made out of silicon. And if you are in the HRC today, don't leave before you go to the clean room. The clean room on the first floor, if you go to that research corridor, the one near the door, you will see the silicon wafer as a sample put on the wall, and you can see how they etch them and make MEMS, micro electromechanical system on them using lithography. So basically that technology of making small things out of silicon wafer is actually very mature, and that's how it dominated the photovoltaic panels. So a silicon crystal will look like this. Those are the nucleus, right? And each one of those lines is an electron shared between those two guys. So basically the silicon, each one has 4 electrons, and it's sharing it with the other 4 around it. So that make those 8 electrons that's basically shared between them. And each one of those electrons, you can, like those 4 sitting around the, by the way, the atom is electrically balanced. So the number of electrons around is matched by the number of electrons outside need to be equal to what inside? Protons, right? So it has 4, it got 4 electrons outside, there's 4 protons inside. Okay, so this guy is balanced, But if you give him the gap energy, and that gap energy can come from, you put voltage across, or you give him photon, you send light. You send photons, and each one of those photons, if he have this energy, if the photon has the gap energy, he will go to the electron, excite him, and the electron will say, oh, look at this energy. Run away. And once he run away, he becomes in the conduction band, and he's free to move now. He's conducting. Okay? So that's how we can turn photons into current. What's a current? Electrons moving. But of course, if the electron is moving like this, we think the current is going this way. So the current is defined as the direction of the positive charge, which is like, if the electrons are going this way, then you think, the current is going that way by definition. Okay, so we will generate current just by giving photons, but they need to have enough energy to jump this gap. Okay, now to improve this process, if only we have more electrons, that would be nice, right? If we have more extra. So this is happening by something called doping. So what is doping? Rather than having the crystal all with silicon, you put either, if you put a material over here that have 5 electrons rather than 4, then the 4 will sit with the other silicon, and that extra electron will be like, where can I go? That's an extra electron. But not that this atom need this guy to be balanced. But the point is that electron is not bound by that band. So we, rather than having 4 in each atom, now this guy has 5. And the more doping we have, the more extra electron that we have. So this material will be negative type semiconductor material. Why is negative type? Because it have extra electrons, because you just did this doping. Okay, we used to have a professor over here. He moved to North Carolina State University. He was electrical engineering, and he was doing a lot. Like, he would take the doping level to really, really high level, because he wanted he was trying to make material that does not even need the sun. You just put your hand on it, and electricity will come. I remember President Harkis, our OSU president, he came to his lab to see those material, and he put his hand on this material, and the light turned on. And President Harkis made the joke that that proved that I'm alive, because if he was dead, he would be cold and he wouldn't really. So he was taking the doping to really, really high level. But the point is, extra electron, that's negative material. What if we put an atom that have, rather than 4, has only 3 electrons? Okay, that creates the opposite of extra electron. That creates something we call a hole. What's a hole? The absence of electron. Okay, so the photovoltaic panel consists of, let's put this guy next to this guy. Let's put a negative type semiconductor with a positive type semiconductor. So negative type is on top and usually thin, and positive type at the bottom, and it's usually thick. This guy has a lot of hole, this guy have a lot of electrons. Okay, so now I bet your question is, wouldn't those electrons go here, fill the hole, and then we are done, and we go back to the nothing? No, because yes, some of them, of course, at the interface, they will, man, look at those holes. You have all those electrons here, and look, and they will come over here. But notice that this was already balanced. Those electrons, those extra electrons, we call them extra, but they are needed for their atoms. So when they come over here and leave that place, they left behind a negative. I'm sorry, they left behind a positive charge. And so that positive charge will say like 1 electron go, that's okay, 2, 4, but then after a while, no guys, don't go. You cannot leave us positively charged. So there will be created an area over here that prevent extra electrons from coming. Of course, if the voltage, if the electrons here are really, really big, the population is so high, then they will cross this and go to their holes. So it requires huge voltage difference to make all those electrons cross that interface area. Okay, but there will be an interface junction. There will be a junction that basically once you deplete that junction, it prevents extra one from coming. Okay, so now under the sun, when you start sending the sun and you got all those photons and those photons come and strike all those electrons, especially the extra one, because of all the doping, then they will be over here. They have two choices: cross this, but they require voltage to cross, or instead go through because you're going to connect. There are conductor on the top and conductor at the bottom, and those conductor come and connect to the load over here. The load is basically the light bulb or the motor or whatever. So it's actually easier for the electrons to go through the load and come to this side rather than cross from here. Of course, if the load again is like really large, they will not be able to go this. There is a maximum voltage and we'll talk about it in a minute. But I just want you to figure the idea. The idea is light excites the electrons. Electrons actually go through the load. And so this is a battery that generate voltage under the sun. When you put the sun on it, you create a lot of electrons, holes, and the electrons are ready to jump through the load. And
I'm looking at people that are in my class because he said our project we could do in groups, and I'm seeing if I recognize any of these people, and I'm going to ask them if they want to be in a group with me.
can you guys mute yourself, please? All right. Question.
So once you get a film between the positive and negative, and then you isolate, is that when it starts discharging?
So we're gonna study this circuit exactly in few slides. So hold your question, and I will show you the inner plumbing of that junction. Okay, but for now, just need to realize that the electrons, it's easier for them to go over here. It takes huge resistance for them to say no, let's go this way. Okay, very good. So how much energy does photons have? And is it good enough? Is it bigger than the band gap energy or not? You use this equation. This equation is the equation between the electric and the energy and the wavelengths of the light. So you know the light coming from the sun is not just one color, it's different color. Each one has its own wavelengths, lambda. Okay? And H, it's the Planck's constant. And C, of course, is the light speed. Okay? So E is H C over lambda. So if you know lambda, you'll be able to calculate E and vice versa. So E, when you cook all those numbers, it's 1.24 over lambda in micrometer. So you know the wavelengths in micrometer, you'll be able to predict E in electrovolt. Piece of cake, right? Now, in order to find out the watt per meter square that's falling, you just need to know how many photons flux, number per meter square per second, and you multiply by the energy of each one of them. Then you'll be able to figure out. It's like the energy per photons and how many are coming per unit time. So that's why the H, or the energy falling on us, would be like 900 watt per meter square. It's the total number of photons multiplied by their wavelengths. But as we see, they are not having the same wavelengths, and therefore they don't have the same energy. Okay, so here's an example from our book, and he's just basically doing this calculation. Okay, so, but he's doing it for silicon. So for silicon, the gap energy is 1.1 electrovolt. What is the wavelength for that? 1.12 micrometer. So what that mean? If the light you are striking with is shorter than that wavelength, will that be able to make electrons or not?
No.
Yes, because shorter wavelengths mean higher energy. Remember, the equation is it's E is 1.24 over lambda. So if the wavelength is smaller than this, that will make, that's enough energy for the photon to move an electron. But if the wavelength is bigger, like what bigger? Like infrared, that is bigger wavelengths. That's not good enough. Okay, that will not work. So different material have different gap energy, and therefore they have a minimum, they have a maximum wavelength that will work for them. Anything less would work. Anything bigger than that wavelength would say, no, you don't have enough energy to work for us. Okay, and unfortunately, you shouldn't, it wouldn't work as a like, can 2 photon help? Like if 1 photon is not enough, if all the light I'm sending is red, can't you just have 2 photons together and then they help each other and kick 1 electron? No. So in quantum physics, this is weird. 1 photon can only lodge 1 electron. You cannot add 2 of them. Okay. So then if we plot the energy as function of the wavelengths, you will find out that things that are 1.12 or shorter will work. And so 1.12 is perfect. This energy is enough to start an electron to move. But anything shorter than this, there is extra energy available, and unfortunately, it's all lost. Like if you have more energy, he will just really waste it. Like he gets thermalized, and just like move faster, but it's still 1 electron. And anything less than this, because the wavelength is bigger wavelengths, less energy, it will actually not work. So you can immediately guess now or think that the efficiency of converting light to electricity is probably very weak. Efficiency is going to be low because of this problem. So how do we fix this problem? Don't use 1 material. Don't use 1 junction. Use multiple junctions. So that light with all its different wavelengths can ignite or basically move electron in different junctions. Okay, and so that's what they do. So every year they update. I've been teaching this course probably since 2008 or something. And every year, I download a new chart from the NREL, and this is the efficiency of converting light into electricity as function of the years. Okay, and the guys on the top, the purple guys, so this is all the the labs and anytime a company or a university research lab come up with new patent or new product, they mark it. Here is the new efficiency. First of all, you can see how is the maximum is like 44. This was the year 2014 or something. I'll show you the next one, the one that I downloaded today, which is like 2020. But you can see that the efficiency is what, like 44%. And also the purple ones are, guess what? The multi-junction. So the multi-junction is the one that have the higher efficiency. Why? Because they can kind of really use all the wavelengths available for them. Okay, but they are, see, 3 junction, 2 junction, 4 junction. Okay. And there's thin film. So people try to make it cheaper. They are trying to make it transparent so that they can even coat it on the glass. Imagine if all our windows are coated with a transparent thin film that generate electricity and kind of like reduce the heat going into our building, right? So anyway, interesting. Look at this new one that I downloaded today. So 2020, and you can see, well, what, 44 now is 47 in 5 years. So, and those are the one that in the research lab. Huh? This is not the one in Lowe's and Home Depot. If you go today to Home Depot and to buy a photovoltaic panel for your RV or camping or something, you probably are talking about 20, 25. So question here and then here, yes.
So what material, is it silicon based or is it?
So we need a junction between negative type and positive type material. So either whatever the base is, you still need doping, right? You need to dope the crystal with another atom that have extra electrons or less electrons, and you make the junction out of those two materials. The positively, negatively doped and positively doped. And that's how the electrons are, there's extra electron to move around between the two of them.
So when you overdope, doesn't the material change to sound like silicon anymore? Other materials?
Yeah, it's called negative type. Yeah, negative type or positive type, depending on, are you doping with extra electron or less? And there are, if you look here, you can read, you know, all the different companies, and you know, this is a global market and everyone is competing to push, but also reducing the price, right? But let's leave this, like the Dr. Kim over here. Dr. Du Young Kim, he worked on those things, right? So this is really in material science, where how can we make new material that is like really friendly to that process? Electrons come, the photon come, electron jump. Big question. Right. So the multi-junction is very expensive, and you probably are, those are like, why we push this limit, although it's really expensive. Well, think about also think about International Space Station. The International Space Station are willing to pay whatever it takes to get 1% extra efficiency, right? Or like if we're gonna do a base on the moon. Today, I just read that Russia and China are building a new base together, but I'm not sure whether it's on the moon or rotating around the moon. So for those extra terrestrial application, the efficiency is really, really important. Also think about like an isolated location, you know, when you are in the doing an oil field you know, job in the middle of nowhere, all your equipment need to run, say, on photovoltaic panels or something. So there are applications where cost is not an issue, right? That's an excellent question, especially for our project. What is the lifespan of the PV panel? Because when we do our calculation, we need, and we equate the natural gas with photovoltaic panel, the natural gas heater will consume energy every single year. The photovoltaic panel, you pay for it at the beginning and then you don't pay anything. All right? You're not going to pay anything. So in order to be fair, we need to calculate the natural gas cost during the lifespan of that photovoltaic. So now we will see the brochure in a minute of some of those models, and you will see how they will tell you efficiency guaranteed for this many years. After this many years, the efficiency will drop to this number. So I actually gonna make it your job to come up with a fair way to make that balance. And remember, in the project, you do the design, but then in the last part, which a lot of people don't do, The last part is that you go and criticize your assumptions. So that's an excellent place where you would say, I assume the efficiency of the photovoltaic panel will run for 20 years like this. And that's how I calculate the cost. Then you can go in the last part and you really investigate this assumption and maybe search a little bit and figure out how does the efficiency drop as function of time. And you'd say, now my assumption was like really horrible, and this will result in this much difference between the number installed and the actual number needed. Or you come to the conclusion that, you know, my assumption was really not that bad. I assumed 10 years, and they say that within 10 years it will drop only to 80%. So I am okay. I'm only going to be off by 20. I need just 20. If I would or design the system 20% extra panels, so if it needs 8, I'm going to make them 10. I'm going to be safe for the first 10 years. All right. Good questions. So this is the sketch we are dealing with. A junction between negative type and positive type. Photons come and the electrons will start flowing. Okay, from the negative type to the positive type over here. Okay, so the plumbing inside here is like this. This is the current going through the load. Okay, so now interesting, when the first picture we looked at, those are bunch of cells next to each other. Each one of those cells have two sides. The top is one material, the bottom is one material. And so you connect the top and the bottom to your load. And if you connect them, so if we open this like they are next to each other, so if you want to connect them in series, you connect the bottom of the one with the top of the second one, right? Like you connect negative with positive, negative with positive. So eventually the load is driven by the current that this photo or this cell basically generate. So it's better to calculate the current density per unit area, because as you see, this thing is flat. It's like 2D kind of. So the current density, how much electron per unit area, is J. Okay, so it's the current per unit area. So now the amount of current that will leak over here, we will call this the junction current. Okay, so the light, the photons, are capable of generating GS. How many of them will go to the load and how many will go to the junction and escape is basically the base of this equation. So G load is GS minus G junction. The total number that you generated because of the light minus how much will escape from the junction is your load. That's the useful part. Okay, so now the part that will go through this junction, there is a lot of explanation in our book, and you can also go online to understand. There is like dark light, dark current, and light that will increase with this dependency on the temperature. But basically, this junction is basically this bracket. Okay, so what does this tell us? That if the voltage is really big, it takes a big voltage to do what? To make this equal to GS. And that will make G load 0. Okay, so what is that voltage? We call it the open circuit voltage. Imagine if we cut this, so now all the light generated, all the light striking the cell will do what? Will make a lot of electrons over here, but there is nowhere for them to connect because it's open circuit. So what will happen? The light will stop coming? No, the light will keep coming, but the electrons will go this way. They will go through the junction. So that is the maximum voltage that you can impose on the on the cell, because at that voltage, they will just go back in and you will have 0. Okay, how much is that voltage? It's not that much actually. You'll see it in a minute. Okay, so how do we get it over here? You just make GL equal 0, right? And so if you do this, you get that voltage. If you make GL equal 0, that's what you say over here. If you make GL equal 0, you will get the voltage open circuit, VOC. That's very important number. Okay, and the other extreme is if we make the voltage 0. How is that possible? If we make the voltage difference between this and this 0, what is that? No, touch them. If you touch them, if you take the 2 wires without a load and you just touch them, if you connect the top to the bottom, that's a short. That will give you the maximum current. All the electrons will like, man, it's like a short circuit, let's go. And rather than going through the gap, they will all just like, let's cross from that wire. You just shorten us. So that is a short circuit current. Okay, so that's the other extreme. All right, and in between, the load would basically be following this equation. Okay, now the power. We are not excited when either scenario is horrible. Open circuit, which is the largest voltage, but 0 current, that I get 0 power. Short circuit, which is the maximum current, but 0 voltage, I get 0 power, right? So my power is GL times V. And remember, actually, the power is IV. If you remember electricity course, the power is IV because it's the DC. If this was EC, what is the power? For EC, it's IV cosine the angle between them, the power factor, cosine phi. I, current, multiplied by V, voltage, multiplied by cosine phi. And the angle depends on is the current is leading or lagging, because your motor is like conductance or inductance? Is it a coil or is it a capacitor? Okay. Anyway, for DC, we need to convert, by the way, and that is a big thing of the project cost too. So you can see that this is all DC, and the heat pump that you're gonna drive with this is probably running AC. The compressor run AC. So we need something to turn the DC generated by those photovoltaic panels, and usually they are designed for 24 voltage, 24 volt. You need to convert this to EC, 110. The device that does this is called inverter, right? And so that is sized by the power. So and also how nice the conversion is. Is it like just like a tooth, sawtooth, or is like really pure sine wave? And when it's like really nice sine wave, they tell you pure sine wave. But anyway, you will size those inverter by their wattage, how much kilowatt they can actually handle. So for DC, which is our panel, the power is IV. So what is GLA? Because GL is the current density per unit area, right? So you multiply by the area and you got yourself IV. So this is what we would like to maximize, actually, the power. Not the current, not the voltage, but the power. So the curve of the photocell is like this. Okay? This is between the current density, the J. He's normalizing a GL by GS. So when GL equal GS, that is the maximum current he will get. Okay, when he shorted, and that's when the voltage is 0. All right. And when you take the voltage all the way to the VOC, the open circuit voltage, which is like what? 0.6 volt. So, I mean, that's even not a single, it's less than this one. So this one is 1.5. So to get 1.5, I need to stack 3 of them together. So I can get 1.5. Right? I need 3 photocell next to each other. 0.5, 0.5, 0.5. I get 1.5 over here. So I'm not gonna run here. I'm not gonna run here. See this, multiplying the I times the V, you get something like this. So where I would like to run then? I should run here. This curve is I times V. This point, this point is the point of maximum power. And the voltage corresponding to it and the current corresponding to it, which would be this current. So this current and this voltage will give you the maximum power. So we call this voltage here VM. VM, the voltage that will give you the maximum power. So if the load is such that he put only 0.5 on each one of those cells, you get the maximum power. If you put higher voltage, you may end up having 0 current coming out and 0 power coming out. Okay? Question about this? Very good. So as we saw earlier, the number of photons striking is related to the power, the instant power, the watt per meter square, right? Because the flux multiplied by the energy of each photon is the watt per meter square. And at the same time, it's also related by the current that it will go. So that curve of how much power is coming from the photocell, I and V curve, you should expect this to go up as we increase the number of photons coming. Or basically, if I open the table and say the watt per meter square in Tulsa is like 600 or 700, and then in Arizona it's 900, probably we can run here and Arizona would run like this, because they have more watt per meter square falling on the. Also, you yourself, if you have your panel like really in the wrong direction or like in the wrong tilt, you're not going to get the right watt per meter square. But if you make your panel always normal to the sun, you get the maximum watt per meter square possible, and you move up here. So the output of the PV panel is related to the incident radiation on it. So when I go to Home Depot tonight, it's probably too late, and I find this panel and they said 200 watt, and for how much, whatever dollars. What is this 200 watt? Always generating 200 watt. You open the small font and you see it's saying electric specification at standard condition. What is the standard condition? 1000 watt per meter square. What did we call this? 1 sun. So he's saying if you give me 1 sun on me, and because we saw that how the voltage, how the short circuit current and stuff, they are all function of temperature too. The equation has temperature. It's also the temperature. You don't make it too hot on me. So 25 degrees C, and that's called the air mass. The air mass is the sun. If the sun go directly in the atmosphere, so it's 90 degrees above us, then that's the shortest distance for the sun ray to go through the atmosphere. That's air mass 1. But once the sun tilts, because we are in Tulsa and we never get maximum angle of 90, then the sun will go through the atmosphere longer distance than the minimum distance. That's the air mass. So he's saying don't do more than 1.5, don't do less than 1000, don't get hotter than 25. And we can guarantee you 200 watt. Sue us. You can sue us if we don't give you 200 watt under those conditions. Actually, no, you can't. There is like, they have a 5% or something. You will see how much off they can go. But the point is, this only happened at 1 sun. Okay, so our job, as we sizing our system, is to figure out, okay, here's 1 sun, and you get your label, the sticker on those panels. Not all panels generate 200 watt, by the way, right? Some of them generate 300, some of them generate 50. How come? How come they generate larger number or smaller number under 1 sun? They are bigger. They could be way bigger, right? They also could be more efficient. They just use like better material. And so even for the same size, they could generate more than the other one, right? And so as you are choosing the right number, the kind panel for your project, are you gonna choose the most efficient or the largest power? Or how do you choose? There are so many in the market. Which one are you gonna choose for your project? What is the criteria for choosing? So many. What should I do? Which one should I pick?
Wasn't it the power per kilowatt or not power, kilowatt hour
So
per dollar? or
let's
something?
get the online first. So what are you saying? Raise your voice.
Saying, isn't it like the kilowatt hour per dollar or something or?
Yes, the cost. Is that Denver?
Yes, sir.
Yeah, so Denver is saying you need to figure out how much dollars per the kilowatt hour you are generating. Or like the dollar per watt, for example, under one sun. So it's really the cost. I mean, if I'm getting 200 watt from a really big panel, but cheaper one, I'm fine. I don't need, as long as my roof allow me. So there is a design constraint. How much roof area do you have, right? So if you are within that constraint, go for the cheapest. Don't go for the most efficient, right? Of course, the most efficient will take smaller space, but is that a big problem or not? If it's not a big problem, that's okay, right? The reason why we don't have solar electric car right now, that was actually one problem in one of the finals. Remember, whether it's last final or the final before. I basically said, I gave them the horsepower for like an average car. And I told them just calculate how much area we need to drive this totally out of solar panel. We don't need battery to store. We just want, when the sun hit, we want to run it. And you can see the area is so huge because the efficiency of converting of typical solar panel is so small, right? So until they come up with like a really photovoltaic panel that are very expensive, not very expensive, very efficient, the area is just really huge to drive just a car, right? But maybe you can drive an airplane. Why? Because the airplane can be a glider, for example. Maybe it does not require that much power to fly it once it's flying. Okay. Very good. So question, you had a question.
Oh, yeah, the one sunlight, is it from morning to evening? Like one sun?
So that's a good question. So this rating, watt per meter square, this is power, huh? This is power. And that the power of the radiation will be constant throughout the day or be different throughout the day? It will be different throughout the day. Why? Why does the sun radiation incident, and I'm not talking about tracking problem, huh? I mean, if you are fixed like this and waiting for the sun to come in front of you, for obviously you will get the maximum radiation when the sun is perfectly aligned with you. But even with a 2D tracking system that's always looking at the sun, you are not going to get the same radiation on that 2D tracking. Why?
The atmosphere.
Yeah, the air mass. When the sun is so low, it travels a lot and it diffuse, right? And you really need to go when it's like really, let alone the temperature also in the environment. So the incident radiation will be varied through the day. And in the homework that we had this week, you were given that incident radiation. The problem was like really trying to make it easy. And he said, you know what, here's the incident radiation. But you guys need for the project to figure out that incident radiation in Tulsa, Oklahoma in your panel. And I can give it to you I have the data, but I am not going to give it to you. Why? Because I want you to be able to leave this course, and wherever you end, Georgia or Kansas City, or I want you to be able to say, I can design this for you guys. I know where to get the density radiation for every hour. Okay, so I want you to find out. I mean, the places are not that, it's either NASA or the NERL, right? So you will find it there. You'll find a data set where they actually have the density radiation for any city or any date. We are really fortunate. We live in the USA because the wealth of data that we have. You know, if this course was like in a very small country somewhere else, we'd be like, I don't know, maybe we should go and measure it because no one ever measured that before. But those things have been measured forever. Okay. All right. So what else we see in this chart? Limited peak power warranty for 25 years. Okay. And I think in the next page, they will tell us what is that limited efficiency. Where does it say limited efficiency? There is a place where they would say, 85% for the first 7 years and then this much for the next year. And I don't see it right now, but it does exist. Okay, but anyway, limited peak power warranty for 25 years. So you can, if you are buying this panel, in the first part of the project, say, I'm going to assume this will survive for 25 years. And then when you dig deeper and you find exactly how does the efficiency drop as function of years, you will be able to adjust your number. Anyway, what else we see? VOC, 32 volt. How come 32 volt? I thought it was 0.5. Why 32 volt? Why? Yeah, they have probably 64 in series, right? So those wire that you see are what? Those are the conductor that they are connecting them. So they probably have, and we will see how many we need in series. And the short current, 7.9, okay? But those are the two extreme points. He's not gonna run at this. He's gonna run at VMP and IMP. What is that? Maximum power, maximum power. Voltage for maximum power, 26. And current for maximum power, 7.51. So each one of those guys are gonna give you 7.51 at that voltage. So 7 times 26, hopefully it's 200, right? Is it? Hopefully, right? Hopefully 7.51 times 26.6 is a 200 watt. Volt time current is power. Good. So now with the temperature increase, you get what? Minus what per degree C. You take me higher than my standard condition, and the penalty is you lose 1 watt for every degree C, degree centigrade. All right. Very good. And so now look at this graph. 1 sun, you get this. 800, you get this. 600, you get this. So a very important thing that we need to learn today is how do we do this calculation? This 200 watt panel under 1 sun, if I put it in Tulsa, Oklahoma on March 21st at 11 a.m., where the radiation is 600 watt per meter square, not 1000 watt per meter square, how much I'm gonna get? Am I gonna get the 200 or I'm gonna get something a little bit less? We need to, this is what we need to get out from today's class before you leave. Okay. So, so the actual power curve, the actual power curve if it's like really a square, sorry, rectangle, if it's really rectangle, that would be ideal. Because if it's rectangle, you get really, really high power because you get the VOC multiplied by the I short circuit. But because the curve is not rectangle, it's basically curved, you get less power. So the difference between what you get and what the maximum ever possible, which is VOC time I short circuit, is a factor. That factor is kind of like the not really efficiency, but how far we are from the ideal case scenario. That FF is the fill factor. Okay, so one can basically define the efficiency as the VOC ISS FF, which is the B max that you will get divided by the input power. That's what is the meaning of that fill factor. How close you are to the perfect rectangle. Okay, yeah, over here. Look at this. So today photovoltaic module are extremely safe with minimal failure rate and projected surface life of 20 to 30 years. Actual performance is usually 85 to 90% of the standard condition. So now how many you need to stack? One cell, and you need to stack them in series and in series for voltage so that you can go up to the ideally the 24. Right? So some system run at 24, some system run at 12. Okay. So you stack them in series to get the maximum voltage, and you stack those series lines in parallel for current or power. So to get the 200 watt, that will determine how many in parallel. And to get the rating that this can work at 24 voltage, that will determine how many in series. Okay, because as you can see, if you connect two cells in series, you get double the voltage and the same current. And you connect them in parallel, you get double the current and the same voltage, right? So here is an example in our book. So again, the photocell would look like this, and that silver or like connecting rod, he's basically connecting the top. Note that he need to be thin because he does not want to block the sun, right? But he still need to be able to pull the electrons from the top, because the electron need to leave from the top through those wires and go to the load and come back to the bottom, right? So here is saying, well, we have all those different junction that we can use, and he gives them the designation AH and AG and AF. That factory make all those guys. Each one of them has its VOC and I short circuit, and more important, those two guys, the voltage at maximum power and the current at maximum power. Okay, and maximum power and their efficiency, of course. Okay? So you can see efficiency like in this 16% and stuff. So what does he want? What does he want? And this is all under solar radiation 1000 watt per meter square. He's saying, I want to create a module that's 12 volts and 120 watts. Recommend the arrangement. So that's a piece of cake. And he said it's AH class. So you come here at the AH class and you say, well, what is the voltage? 0.49. Okay. You want 12. So 12 over 0.493, that's how many in series. Right? And you want 120. Well, figure out how many you want in parallel. So that's the solution. 120 divided by the 2.5. So actually, let's do this one first. So 12 voltage in series, 12 volt total over 0.493, you get 24.3 cell. So how are you gonna do 24.3? You're probably gonna do 25, right? So you do 25. Now, how many in total? You would say, well, I want 120 watt divided by the power of each one. You get 47, which is 50. So it's obvious 25 and 25. Put them in a big panel, and you're done. Good. All right. So this is a good time to stop for a break. So let's take a 15 minutes break, and we will see then when you put a system like this, those ideal panel that's supposed to work under one sun, when you put them in an actual system, what do we do and how we can predict what they will do. Okay, so let's take a 15 minutes break. We start at 27. So we should go to 42. 1 minute. All right, it has been 15 minutes already. So online, can you guys still hear me?
Yes, sir.
All right, thank you. All right, so what we need to understand now is if you buy, say, a 36 kilowatt of PV panel, that's the installed power sitting on the roof. So maybe you put how many? 36. So maybe 72, each one of them is 500 watt. You will be able to get this. So putting the 72 panels, each one of them is 500 watt on the roof. How much energy will it actually produce every single day? So he's saying so far they generated this much kilowatt hour. So the energy is in kilowatt hour, the power is in kilowatt. That's every second you generate this many joules, you multiply by the number of hours and you get the total kilowatt hour. If I want to calculate how much money did this guy generate for me, all I have to do is multiply this by roughly 11 cents or 10 cents. So during the time this thing has been sitting there, he generated $31,000. Right? Because every kilowatt hour is like 10 cents. So hopefully in the lifespan of this project, you get back the price of those 36,000 panels. Right? Now, if you look at so actually it's 63 kilowatt, I'm sorry, 63 kilowatt, but right now he's generating only 36 kilowatt. Why? Why is not installing or generating the rated power? Because maybe in New Jersey at that time, sun is not perfectly aligned on those panels. Maybe he's not getting one sun. So the fact that you're not getting one sun mean that you are not gonna get your installed power. So it's like, what's 36 divided by 63? That's like, what, 65% or something, right? And if you notice, so this is the lifetime of the project, or like so far. You can do it per today or week or months or year. So those panels actually come with a software usually that monitor them, and you can see the performance even from far away. If connected to your wire, your Wi-Fi, you'll be able to always check on your panels how they are doing and how hot. Cell temperature. Okay, you can measure the cell temperature. You can measure the ambient temperature. Right. So anyway, so what is this cycling? What is this cycling? Yeah, winter, summer, winter, summer, winter, summer, winter, summer. So you can see how many years he has been working. Okay. And also that tells us that if we are designing this thing in the summer only, we will be installing very few. And if we design it over the winter, we will overshoot in the summer. We will basically have too many panels to do anything with them in the summer. That is the problem with solar radiation. The sun is not as available all year long at the same level. So for this project, I'm gonna make it easy because it's only 10% and it's not really a big deal of the course. So I'm gonna say just design this for the spring March 21st. But in part 5 of the project, you can say, now, if we actually use this design, we will really suffer in the winter, or this is how much we will suffer in the winter. You can figure out from the data that you get for Tulsa, Oklahoma, what is the difference between the radiation in the winter compared to the peak of the winter, compared to the 21st of March. And you would say, you know, we based this thing based on 600 watt per meter square, but in the winter, in the middle of the winter, this number can drop to say 400, and that will make us short by this much, for example. So the last part of the project, when we criticize our own assumption, you can use this part and say, now realistically, I should have based it on the winter to make sure that I have everything, or maybe I should just be ready to supply the power from somewhere else in the winter, because I don't want to really put so many that will be useless in the summer, right? Very good. So also notice that he's calculating how much CO2 he has been saving. How do you do that? If you figure out how much power you did generate from the sun, then you can basically assume an efficiency of the thermal power plant, like the Jinx power station or the Owasso power station. You know, this one is 65, this one is 40%. And you tell yourself, if I'm generating this power from Jinx and the efficiency is 40%, then the amount of joule BTU required from the natural gas that will fire the boiler of the power plant would be this much divided by 0.4. That will tell you how much BTU is required. Now we figure out what is the heating value of natural gas, how many kilojoule per kilogram. You will figure out how much kilogram of natural gas H4 I need to burn to generate those BTU. And if you figure out how much kilogram of CO of natural gas you are burning, using that equation, the combustion equation, which we will study later, you will be able to tell for every kilogram of CH4 how much kilogram of CO2 is being generated. So all this is embedded in that number. So just by looking at this, they can convert this to how many pounds of CO2 did they save by generating electricity from the sun rather than from burning natural gas. Okay, or even worse, if you burn coal. So if you burn coal, that ratio of how much CO2 is liberated per kilowatt hour generated is even bigger. And again, we're gonna calculate this later on in the course, don't worry. So now this is another, so this was what? Melbourne, New Jersey, and this one is Eatontown, New Jersey. Now this is per year, and you can see the variation between the winter and the summer. So this is dramatically drastic because probably they're using just a flat surface. That is horrible. At least you need to in the winter to tilt, right? Because in the winter the sun is so low, and if you are flat, you will not get anything, right? The sun will just bounce, especially if in New Jersey, and that's a little bit north. So that means that alpha max is even smaller, right? And so that's what you will get if you don't adjust the angle, I guess. So what we need now, the really important thing to learn today is this, the regional factor. Okay, what is this regional factor? If I divide the kilowatt hour generated during this month, not this is historical, but if I generated the kilowatt hour generated per month divided by the kilowatt installed, what that number represent? This 75, if he generated 17,000 kilowatt hour during March, and he have 236 kilowatt installed on the roof. What does this number represent? A kilowatt hour per month divided by the kilowatt installed. Anyone?
How many hours you can run it?
how many hours you can run it, or did you run?
Right.
How many hours did you run it, right?
Yeah.
How many hours did you run it? No, I need something more specific than this. Because it's running all day long. Those photovoltaic panel is sitting on the roof all day long. So what does, so you are right about something. The unit of this is hour. This is
How many-
70,
How
this
many
is
hours you
75
can?
hour. The answer is, how many hours have you been harnessing the sun? No, I need something more specific than this. What is those 75 hours?
How
Anyone?
many hours at 236 kilowatts that you?
Yes, yes, but there is a nicer way to say it than this. How many hours of,
Peak power?
no, how many hours of, no, how many hours of one sun did New Jersey get? So the weather in New Jersey is such that during that month you get 75 hours of one sun. Of course, you didn't really get 75 hours of one sun. You probably got 150 of half sun, or actually better distribution is you got this much quarter sun, this much half sun, this much one sun, this much quarter sun, this much. But in total at the end is it boiled down to this. When you put those panels in New Jersey, it will be such that you get 75 hours of one sun. You multiply this by the number of kilowatt installed, and you'll get your kilowatt hour. So this is very nice number, the regional factor. If I know the regional factor for Tulsa, Oklahoma, I multiply this by the sticker on the panel that I'm gonna get from Home Depot, and I would know exactly how much kilowatt hour I'm gonna get from this panel sitting on my roof, assuming that I'm eating this energy all the time and it's not being lost. Okay, so we need to know that regional factor. That regional factor could be hour per month, or it could be hour per year too, right? I mean, you can get the regional factor per year. Does this make sense? So the kilowatt hour you get during this period divided by installed power will tell you the hour per month or the hour per year. Okay, so number of hour per day of full power output, or basic number of hour of one sun. So again, thank goodness we live in the USA and we have the map for the regional factor. So this is, what do you think? What do you think those 800 for Tulsa, Oklahoma? Those are, don't look, I don't want you to read, I want you to guess. What do you think those hours are? One sun per year. So total, how many hours we had? We know that from wind energy. How many hours we have per year? 8,760. You cannot forget this number, 8760. Out of the 8,760 hours per year, at least half of them are night, we are sleeping, right? And the other half kind of, I mean, we should get 400 of sun, but no, we get 1,800. Okay, but like Arizona and New Mexico, they get 2,000. So that difference, you can translate this immediately into dollars, because the kilowatt hour is this number times the panel. So if you put a 1 kilowatt panel on your roof, you multiply by this. In Tulsa, you multiply by this if you are in New Mexico or Arizona. All right? Good. So many times the final exam will have a problem just get solved by this number. I tell you, here is the regional factor for the city. Calculate how much kilowatt hour you will get. You multiply this number of hours times the rated power on the sticker, and that is the kilowatt hour generated. Okay. Again, when you look at a map like this, you would think that everyone at the same latitude should get the same regional factor, but it's not, because of climate, cloud, rains, right? Humidity, maybe elevation a little bit if you're closer to the, but you need really big difference. You need big difference to be a little bit higher so that the air is not that much and the sun radiation is like really stronger. Photovoltaic. All this chapter is about photovoltaic panels, how we turn the photons into voltage. Okay, got it? So in order to figure out how much kilowatt hour per year, all we need is the regional factor time the rated power. If I want how much per month, I multiply the number of hours per month. So maybe you guys can find a better map that will show the description or the division of those hours per month. So you would see in March how many hours, in December how many hours, right? And then you can divide this over the number of days per month so that you can figure out how many hours per day during March. So during March 21st, how many hours of one sun that we get? Okay, very good. So this method is very convenient, but what's wrong is that it's not hourly. Like I wish I can see the performance of the photovoltaic per hour, rather than just like here's the average per month. So there are models that will be able to tell you this. Okay, but this is very convenient to do it per month. Okay, so now if I want to do it per hour, especially that, what is wrong also with this method, guys? What's wrong with this method? Why you don't wanna risk your career on this calculation? Tell me something bad about it. And so it is very broad, it's over a year. There's no seasonal variation. I mean, we need to see what happened between winter and summer, but what else is bad? Where is the collector in this calculation? Is that for a horizontal collector or tilted collector, or is it a 2D tracking collector? Like, where is the collector in this calculation? Maybe I'm so stupid, I'm gonna put my collector facing north, for example. Will I get this? No, you're not gonna. So where is the collector? How do we do this? So this second method do that for us. What this method is gonna do? This method is based on the idea that the efficiency of the collector is function of how much radiation is falling on it. Yes, we know that. If you have one sun, you get the rated power. If you have less than one sun, you get less and less and less. Okay? But basically, the output, if you remember at the beginning of the lecture, the output was really related, the watt per meter square is related to the number of photons striking. And the number of photons striking is equal or related to the number of electrons striking. So the output power is really related to the I, just like one-to-one relation. There is no radiation square or radiation cube or anything. It just, the power output is related to radiation. So the way to do this is to say that, what's the sticker power, the rated power you have on the panel? 160 watt, okay? Only at one sun. So if you know what is the radiation right now, so this day, March 21st, that we are stuck on. So if it's at 11 a.m., 11 a.m., it's 800 watt per meter square. How much power will come? What should I do? I want to know how much power is going to come at 11 a.m. when the output power, sorry, the incident radiation is not 1000 watt, but instead 800 watt per meter square. What do I do? I should multiply 160, which is the rated, time 800 divided, don't look here, 160 watt multiplied by 800 divided by 1000. What did I do? I am basically telling myself it's linear proportional. So I'm dividing over 1000 to normalize it and then multiply by 800. That will work. That will tell me it's not 160, it's going to be 160 times 8 over 10. How much is that? Can anyone help, please? 16 times 0.8. How much? How much? 120? What? 128. So at 11 o'clock, assuming it stay at 800 watt per meter square, I'm going to get not 160 watt, but 128 watt. 128 for 1 hour, assuming it stays the same, then that will give me 128 kilowatt, right? Kilowatt hour, 128 kilowatt hour. For 1 hour, I'm going to have 120, did I say kilowatt? So 0.126, then 0.128, because we need to divide over thousands. So I'm going to get 0.128 kilowatt hour during this 1 hour. And then at noon, let's assume that it go to 900 watt per meter square. How much output power I'm going to get? 160 times 900 divided by 1000. And we do the calculation, and let's say it's like, I don't know, 145 or something. So I'm going to get, if this lasts for 1 hour, I'm going to get 0.145 kilowatt hour during this 1 hour. And so I need to keep multiplying by the incident radiation and add the hour. Incident radiation and add the hour. Incident radiation and add the hour. So then by the end of the day, I will get the kilowatt hour generated from that solar panel. And this is really more accurate because the incident radiation on the panel, whether it's 800 or 900 or 700, is really a function of, you can calculate this by cosine theta I, the incident angle. So if you know what's the normal radiation coming to the normal direction, you do cosine theta I, depending on your tilt, and you figure exactly what is falling on your collector. So that power falling on your collector divided by 1000 times the rated power is what you're going to get for that 1 hour until the sun changes its position, the cosine theta will change, the incident radiation will change, you get the new number, then you divide over 1000 and multiply by 160. And when you add all those, how many incident radiation, how many incident radiation, how many incident radiation, at the end, you will realize that what you did, every time you multiply by 160 over 1000. So if you pull 160 over 1000 away, what happened inside this bracket is the power in the first day, in the first hour, and the power in the second hour, and the power in the third hour, and the power in the fourth hour. If you add all those, you come with one number, and that number is the kilowatt hour per meter square per day. So rather than doing it instantaneously like this, if you multiply times the kilowatt hour per meter square per day, you will be able to figure directly how much kilowatt hour per day is coming from that guy. So to recap, how much kilowatt hour I'm going to get from my panel, the sticker, divided by 1000 watt per meter square, that's always constant, time the kilowatt hour per meter square per day. How do I get this number? Well, can I do this? That's my resume. So you come over here, this table, what this table tell us? The kilowatt hour per meter square per day, say during March. For latitude tilt, the average is 4.5. So here, 5.2. If this is setting a latitude tilt in March, you get 5.2 kilowatt hour per meter square per day during that month. And depending on, are you latitude minus 15? What's latitude minus 15? Mean that the tilt of the plate is not 36. It's 36 minus 15. Why would they do this? Because they want to go down because it's summer. So they go down for it. Or you go latitude plus 15. And you go this up because it's like winter and you need to go up because the sun is not that high. So whatever your latitude, you get the kilowatt hour per meter square per day, and that's what you have over here. Okay, does this make sense? Rated power from the sticker times the kilowatt hour meter square per day, divide by 1,000, you get the total. Of course, if you have this number per hour too, you can calculate the kilowatt hour every hour. But if you have this number as just like one number for the whole day, that still work. Okay, so first method, let's just multiply by the number hour per year, and we get the average per year. The second one is like, no, you can do it every month if you can just figure what is the kilowatt hour per meter square per day. And you can do it even every hour if you know exactly how much is the incident radiation every hour. Okay? Tell me now if you're confused. Why we are doing it like this? Because we know that the number of electrons is proportional to the number of photons, and that's proportional to the flux, and that's proportional to the incident radiation. That's why the relation is linear. Okay? The third method, which we are not going to do in this course, let's leave this when you go to grad school and you are doing more sophisticated analysis. But you can actually use the equation of the cell itself, its temperature, its incident radiation, to calculate its instantaneous efficiency. That's why in the software they tell you what's the cell temperature and what's the, right? So there are equations like this, which basically tell you we have like a reference efficiency, but that reference efficiency will get dropped depending on how hot you are and depending on the load that you got, because if you pull current from us, we can, so this is radiation. So you can modify the efficiency by the temperature and the incident radiation that's falling on you. Okay. Questions? Yes. There is penalty on the temperature, right? And so there is, and that's a chance for you to win the innovation award. How can we make it so? How we can, because we are not going to invent photovoltaic panel in this course, but how we can make it favorable for it. How we can, maybe the water need to cool the panel as it goes through, for example, or something, so that maybe we can put it in water. I don't know, maybe that we need to design a new heater where the photovoltaic is sitting in the water bath. But you can see that chart over here. The power is minus watt per 1 degree C above the reference. So you go 10 degrees C and you basically lose 10 watts, rather than this guy is running at what? Did you run 200? You'll be 190, for example, for 10 degrees C. So what is the relation to geothermal? What do you mean? Yes. So photovoltaic are used in, unfortunately, not that many places over here. When the last time I flew before the COVID-19, I landed in Indianapolis, and the airport was covered with photovoltaic panels all over the place. I mean, you don't see that over here. Also, on one trip I went to was it New Mexico, California, and the parking lots of the cars of the university was all photovoltaic panels, because why would you park your car in the sun? So they covered the parking lot with photovoltaic, that the cars get the shade and the university get the air conditioning for free. So they exist whenever sun exists and whenever the people are interested in generating power from the sun. So Now, how you can combine them with geothermal? I don't know. You guys, we actually gonna go. So I told you next week we're supposed to go nuclear, but we're gonna do geothermal because that's the part where we talk about the heat pumps and how exactly what you said, that the heat pump work more efficiently when you get them cooled by the ground rather than by the air. So we call it ground source heat pump rather than air source heat pump. So the one that we have our house is cooled by the air. And that's okay, but if you put it in a medium that's even more favorable, and the ground is more favorable because it's warmer in the winter and it's colder in the summer. So the air conditioning doesn't work that hard because it's not as if he's trying to cool your house with 90-degree air. No, he's cooling your house with, 65-degree ground. That's pretty cool. It does not work as hard. But I think there's room for you guys to come up with like really new concept. And since this is a paper design, it's so easy to become imaginative. It's not like we really have to 3D print this or assemble that. So let your brain go wild. And I'm not trying to set an unrealistic expectation. I need you to know that one of my undergraduate students, he was taking the course and he got excited about the thermocycle, and he came up with an idea that improved the efficiency of refrigeration cycle, and he submit this to the national competition for innovations. They call it Collegiate Innovative Award, and he ended up picked as the top 5 in the nation. And the competition was from MIT and Georgia Tech and Illinois and Oklahoma State University at Tulsa. And of course, everyone like in Stillwater and Tulsa, everyone like put it in the news. And so he was there with his advisor, Dr. Saleh. And we were so proud. And then he became, fortunately, he became a graduate student. It's Andrew, my TE previous TE, and now he's working full-time as a research assistant for me. So what I'm trying to say that it's not really that hard to come up with really good invention. I mean, of course, you need to be smart, but it's really more important, you need to really work on it. You need to work hard and spend the time. Okay? And he didn't really make a prototype. He just came up with the concept. And that was good. That was innovative enough to be picked as the top 5 in the nation. Okay? And so still now, they still ask me to become a evaluator for the next year and next year. So they asked me to read the other competitors. So I'm hoping one of your team or one of you guys can come up with really a concept that is very unique and new. Okay. And if you don't win the nation, at least you win the Tulsa competition. Let's win against TU and ORU. That's not that hard, right? At least let's win this one. All right, so I'm saying you can calculate the instantaneous efficiency of the cell if you know the temperature of the cell and you know the incident radiation. There are equations. Of course, they measure those on the cells and they can tell exactly how it will behave. But we are not going to do this. So what we're going to do is either this rough method of what is the regional factor or this method, which require you to calculate how much is the actual power falling right now on that cell. You can do it every hour, to calculate this number, or you can pull it from those tables to figure out what is the average per month. Okay, the average, the daily average, the monthly average daily radiation, the monthly average daily radiation. All those are kilowatt hour meter square per day. So they are the daily value, but they are monthly average. During the whole month of March, what is the average? And you can see how this is the temperature, by the way. This table, actually, I'm putting this for you in the homework because I wanted you to see the temperature. So there's a daily minimum and there's daily max, record low and record high. Let's not worry about them. But I mean, we can use the daily minimum and daily max. So you can easily assume the daily minimum happen at midnight, and you can assume the daily maximum happen, say, at noon or something, or like maybe 3 p.m. and 3 a.m., and you just make linear relation between them. Say I will start at 3 p.m. at this thing, and I will finish at 3 a.m. with that number, and I'm just gonna draw a straight line between them, and that will allow me to estimate the temperature. That's a not bad assumption. Okay. Good. So now when we put those photovoltaic after we size them, how we can arrange them? If the load is DC, that's perfect. DC and DC, we are done. Okay, what is DC load? Pumps. We actually, downstairs in my lab, yesterday we were trying to buy a pump to run a desalination experiment. And the pumps that we're gonna buy is DC. So my student said, don't worry, I'm gonna make the converter between EC and DC for it. Hopefully he will. But there's a lot of pumps that run DC. So if you have a cattle or a farm and you just, all you need is like pull the water for them in the winter, because if without water, they will get sick or freeze. All you need is photovoltaic panel and DC pump, and this thing will run. And what's nice about this application is that the storage happen in the tank where you pull the water. So when the sun is there, the water is pulled and it stay in the tank for the cattle to drink. And when the sun is not there, the water is already stored. So you don't have to run all the time, right? You just run whenever there's sun, water accumulate, and people can drink it at their leisure. Now, if you have an AC load and DC load, you need to run it through an inverter, okay? And again, those inverter, you can just check their prices, but they are based on their kilowatt. So if in a lot of problems in the homework, you will see, you would say, we have a house, he has this fridge, he has this furnace, he has this air conditioning, all the power is, all of them require this much kilowatt. So, and figure out how many panels and how many batteries and how many inverters. So you will pick the inverter based on the peak kilowatt, because you need to be able to convert. Now, because photovoltaic only run when the sun is here, you always need with them some kind of storage. Okay. So you need batteries to store this energy, so then you would run at night. In our application for this project, we are saying we are heating a swimming pool. So maybe we don't really need to heat it at night. I will make in a statement that we say we'll run from, say, 9 to 9, and that's it. So, but in other application, of course, you need to run at night. If this was a house in the middle of nowhere, they need electricity at night, right? So we need to figure out how many batteries do we need. It's not that simple. So panels running DC, going to inverter, right? And the inverter take you to your appliance that's running AC. Now, if you don't store in batteries, you can store in the grid. And I have friends in California, the company came and installed the panels for them for free. Like actually, the panel belonged to the company. So they just give them the roof, and they put this, and then the lease is such that, they get some of the electricity for free, and then the rest get pumped into the grid. So in some state, that meter go back and forth. If you generate more than you use, you actually put it in the grid. And when you actually need more, like in winter or like at night, there is no sun, then you take this way. So this meter basically keep going back and forth. And then at the end of the month, they figure, did you use more than you consumed or less? And that's how they count the price. Of course, this is a little bit controversial, because to sell and buy from the grid, that means that the grid need to be able to handle your variation. And for the grid to handle your variation, up and down, the grid need to be ready to supply you in case the sun really go down. And so who's gonna pay for that installed capacity waiting for you to say, please give me electricity? So then they cannot treat it, they cannot make the pricing the same. So when you sell 1 kilowatt hour, you shouldn't really expect the same price when you buy 1 kilowatt hour. Probably when you buy it should be more expensive than what you sell. That's only fair. And if they don't do this, well, the company over here is not going to lose money. Then the company over here will have to make the other people without photovoltaic panel pay. So when they do the scheme, sometimes people will think, well, the people without photovoltaic are actually subsidizing the people with photovoltaic if you have exactly the same rate. But let's leave this for economics class, where what is the fair pricing for selling and buying? I think in Oklahoma over here, they will allow you to connect, but I don't think they buy from us. I think they just allow you to dump on them and they sell to you, but they don't buy. I'm not really sure exactly, but yes, we can connect for sure, but don't expect the same pricing, or even don't expect, I think we need to investigate this further. I don't want to say something that's not correct. But different states have different policy on buying and selling to the consumer. Okay, but in ideal scenario, you know, they will be able to buy and sell. And in ideal scenario too, the whole country will be connected, so that when the people in the East Coast need the sun, for example, or they have the sun, but they don't have the road, they will be able to supply it to the other people. So like especially in a country that's long enough, that would be ideal. So the sun is always hitting one section, right? And that one section is supplying the rest, for example. Anyway, it is actually expected in the USA that the solar radiation will go above the wind energy sometime in the future. Okay, so we need to figure out how many panels, the price of the inverter, and if we have our own battery, how many we need. So how many battery do we need? It depends on how many kilowatt hour you want to store. So some system, one of the previous students that we had in this course, he actually worked for Tesla right now, and he actually live in Tulsa. And at 1 year, I asked him to come and give a lecture over here about how do they design system. He actually design and build the charging station, electric charging station on the highway, so that if you have a Tesla car, you can find a charging station all over the place. They want to build like a big network of charging station. So they will tell you that the standard is that your battery need to store multiple days, a week worth of charge. That is huge number. So depending on how many days you want to store in those battery, and you will see now why they store extra days, because it turned out that if the battery handle, say 600 watt hour, or 0.6 kilowatt hour, so the battery stored joules, not kilowatt or megawatt or watt, right? The battery store joule. So when we calculated the cell power, we said IV. That's power, that's watt. But to calculate this guy is in energy. That's not the 1.5 volt time the current. You need to also multiply by the time. So they call it the ampere hour. So when you multiply the voltage time the ampere hour, you get IV hour. What do you get? If you multiply the current in ampere time the voltage time the time this thing will run, what do you get? What do you get? You get watt hour. Voltage time ampere time hour, you get the watt hour. Okay, so that's why when you want to compare, is my Mac is better than the Samsung battery, or you need to check the voltage and the ampere hour. if you multiply those guys together, the voltage times the ampere hour of the battery, that tell you how much watt hour is being stored, right? Of course, how many hours does this really last, depending on how energy hungry this laptop is. Yes, I have more, but if the processor is like really eating energy, maybe he will not last as the other guy. But the point is, the battery capacity is in watt hour, huh? Or voltage time ampere hour. And so they give you the voltage and ampere hour. And it's nice when it's like ampere hour, because it kind of tell you 50 ampere hour. That means it can run, 5 ampere for 10 hours, for example. So it turned out that you cannot put all this charge and suck it completely in one day. If you do this deep recycling, the battery will not last that long. So the depth of charge and the number of cycles this battery will survive is like a table like this. So if you only every day take 10% in and out, you can survive 5,000 days, right? Because each cycle is 1 day for the solar radiation, right? You charge at night, and you basically charge in the day, and you basically eat from it at night. And if you do 100%, you only survive 450. So it must be there is an optimum, because what happened at the end of the cycle, we need to throw the battery and get a new one. So depending on the price of the batteries, right? Then you'll be able to figure out what is the optimum, right? So they call them deep cycling battery. Those are the ones that are really good for the solar radiation. So I think I don't really know what is the best one, but if you just Google online, you will be able to see a lot of battery recommended just for solar radiation, for solar system. But you need one that is like really deep cycling. Okay. But the point is now, so that's why then, if you assume I'm gonna store 4 days worth in my battery, you are really saying, what is the scenario where you need 4 days without sun? It will not really happen. But you are basically saying that in regular scenario, my battery will run only 25%, because I'm having battery that is 4 times the load. So I'm having like 10 batteries, I actually only need 2.5. But because I'm having 10, because I'm starting to store 4 days of my consumption, every battery would run 25%. And in the worst case scenario, when we have a cloud cover or something, for 4 days, I'm okay. My battery can give me energy for 4 days. I'm okay. So when it happens one time per year, or months, that's okay. It's not a big deal. But during the regular scenario, it's all every one of them is just being run 25%. Okay. So here's an example. So how many of those battery on this table, East Bend Deca battery, you need to store and retrieve 10 kilowatt hour per day for 4 days for a solar PV system. So he's storing 4 days. Again, worst case scenario, and in the best case scenario, each one of them will be stored only 25%, right? So how do we figure out how many batteries we need? Well, here is the load, 10 kilowatt hour, okay? And you multiply by 4, so you actually need to store 40 kilowatt hour. You come over here and you figure out how much does each battery store, okay? And you divide this over the, where? So he decided the depth of charge, he's gonna set it at 50%. So 50% for each one of them. So then he's really storing 8 days now. So 50%, and the battery storage capacity is 80 kilowatt hour. So you divide the 40 over the 80, multiply by 0.5 because you wanna only use half of it, and you will be able to get the number of batteries. Does this make sense? So the load that we want divided by how much each battery will store. He figured out that each battery will store 15.3 kilowatt hour because it is 1,275 ampere hour times 12 volts. So that's the storage of each battery. So now what's confusing is, where do you put this 0.5? Do you put this 0.5 over here? How do I put over here? If each battery is storing 15.3 kilowatt hour, then I'm only storing half, then I would say it's 7, right? 7.6. So I will divide 0.5 over here, which turned out to be multiplying over there. Or you can actually change it over here. So the depth of charge can be either you maximize the load or you shrink the storage of each battery. At the end of the day, it will be the same calculation. Okay? Make sense? So what he did, I think this is more confusing because he said, well, I need 40, but because of the depth of charge, I'm gonna imagine that I'm storing 80. So he did 80 over 15.3. If I am the one doing this calculation in my brain, it will be much easier to think, here is how many I want to store, 40. So I'm going to put 40 over here, and then I will divide over only half of this battery because he said each battery set only store half of it. That is more clear to my head, but it's exactly the same calculation. It turned out 5.2 set he needs. All right. So those problem would be like the typical problem would be a house like this with all those appliances, and we tell you the number of days that you will store. So you will calculate the rated power and you pick the inverter based on it, and then you calculate the kilowatt hour and you size the battery on it. And you also size the number of panels too. Because the number of panels, in order to need this kilowatt hour, what do I need? I need the rated sticker, and I needed the kilowatt hour per meter square per day. And that will allow me to tell how many panels do I need. Because this is how much is coming from one panel. So if I do this calculation, we said what in March, this number was 5. So let's imagine 5. So 160 times 5 over 1,000. Someone please. What is 5 times 160 divided by 1,000? How much is that? 5 times 160, let's call it 930, is it? 800, right. So 800 over 1,000 kilowatt hour per day. So that is 0.8. So 0.8 kilowatt hour per day. 0.8 kilowatt hour per day from each panel, assuming radiation of latitude tilt at Marsh in Tulsa. So 0.8 kilowatt hour per day from each panel. Now, how many kilowatt hour does this house need? You calculate how many appliances they have, total kilowatt hour, and each panel is giving you 0.8. That will tell you how many panels you have. Okay. Good. Now, the inverter, unfortunately, has also its efficiency. Okay. And that also reduce or make the batteries and the panels a little bit oversized. You need to make them a little bit bigger so that if they lose a little bit electricity in the inverter, they are okay. So you're gonna divide over the efficiency of the inverter to figure out the size of those guys. Batteries and the panels. Yes.
If you're making a house from scratch, would you not do a couple of floors down from batteries and then make the house?
Say that again.
What?
Say that again.
If you're making a house from scratch,
Okay.
rather than giving it Would you mind take down and put batteries rather than keeping everything?
So the question, let me repeat here. So the question is, if you have a choice from start designing your house, don't you want to just put batteries and store everything in your battery and get it and just make your house independent of the grid? That sounds ideal scenario, but you need to realize that batteries are really expensive. So the reason why people want to connect to the grid is because they want to save on the battery price. And so one thing that people are excited about is that Elon Musk is promising that he's going to make those new batteries for houses that are so cheap. And once we have this, then we can run on solar. So really, the batteries are really, really expensive. And as mechanical engineer, and again, here's a chance for innovation. Our job is actually to store energy. I think of myself as a mechanical engineer. This is the most important thing in our field. We are supposed to store energy and retrieve energy. And as I told you, the previous Secretary of Energy under Obama in an SME conference, American Society of Mechanical Engineering conference, he said that really the best storage should be hydropower. We should have like a big tank in our house in the second floor, put the water up when we have extra energy and let the water go down when we need the energy, and this will run a pump turbine combination combo that you get power from and in and out. But my point to your question is that batteries are expensive, and so if you can avoid it by another way, it's actually a big deal. I mean, why electric car is expensive? Batteries. I mean, that is a problem, right? But they are working on it. A lot of people are working on this, and I think many countries too trying to build those like batteries facility. Okay.